Okay, so I'm really grateful to Valentina and all organizers to give me the possibility to present this talk for the public, who are really professionals in the lattice quantum field theory, because the talk will be about the lattice, and namely about Young-Mills. I will essentially, it's based on the works on a couple of works written with my great student Zhechuan Zheng, who will be in a few days, who will become a doctor of science in a few days, and of course, especially the computer part, the computer realization was entirely his work. Okay, so what is Bootstrap and why should we do Bootstrap for lattice Young-Mills theory? Monte Carlo is so far the only universal and systematic numerical method to compute non-perturbative functional integrals emerging in quantum field theories and also in random matrix models. And it's time probably to look for alternatives. At least intellectually, it's important to have alternatives to compare approaches, and this makes us more sure in the existing results. And Bootstrap is a new, more analytic approach which applies the methods of optimization theory and gives rigorous inequalities on physical quantities. At least on the lattice, the inequalities you get on physical quantities are really rigorous. It's applicable to a large variety of multiple and functional integrals, greatly inspired by conformal and S matrix Bootstrap, which you heard about, this very precise computations of critical exponents of three-dimensional Ising model, etc. And I should say in this audience, Ising model. Then more recently, it was applied to it was applied to large N multi-matrix models, and this will be one of the topics of this talk. And also, of course, the biggest hope is to Bootstrap in lattice Young-Mills theory, which was probably the idea was proposed in some very early ideas. Prototypes of this method were proposed in these papers of the 80s, and then Anders and Kruchensky recently. And we think we propose now a scheme which is working, at least to some extent it's working. It really gives not only qualitatively, but sometimes quantitatively reasonable results for Young-Mills theory in 3 and 4 dimensions. The method combines McCain-Comigdal Schwinger-Dyson loop equations, the sort of Schwinger-Dyson equations in the loop space, and also positivity of correlation matrix, which implies the application of optimization theory. Okay, let's first explain a simple example. This will be a single integral with this measure which contains quartic and quadratic term, and we want to compute the moments of this distribution. Then obviously we have what we can call loop equations, namely the equations which stem simply from the invariance of the measure with respect to the shifts x to x plus constant, yes, or simply implying the derivative, the full derivative under this integral. So you get this chain of equations on even momenta, odd momenta of A0 by symmetry, and then what is positivity condition? So the loop equations are first ingredient here. The second ingredient are positivity condition. It comes from the obvious inequality. Let's average sum of powers of the variable with arbitrary coefficients alpha. And of course, this is a quadratic, a positive definite quadratic form by construction. Then if you write it in terms of a matrix of quadratic form, it looks like that in terms of momenta. And now this matrix should be positive definite, so having no non-negative eigenvalues, or another criterion is just the positivity of all main minors of this matrix. Of course, ideally, this would be enough to fix completely the solution, but since we have finite possibility, finite resource, finite computer resources, we can only take a finite number of these moments, and the method will concern the moments up to the highest one, up to some highest one. This will be our cutoff. Namely, we take only a part of this matrix. We take the minor lambda plus 1 to lambda plus 1, which we call W lambda, where only 2 lambda, the maximal moment has the order 2 lambda, like W4 here. And we impose the positivity. Then we simply use the semi-definite programming, which you can find this even in Mathematica. And you find the maximum and minimum of, first of all, you express all the entries as functions of the lowest moment, W2. It's possible in this simple model. If you look at these loop equations, you can always do it. You can fix the highest lambda and then express everything through all these moments through W2. So W2 will be the quantity to Bootstrap. So we do it imposing the positivity of this truncated correlation matrix, and we find the maximum and minimum, which, for example, for very generic case G equals 1, the coupling in front of quartic term, and lambda equals 10 already gives you 6 digits of precision with respect to the exact result, which can be expressed through various Bessel functions. And one can show, one can prove rigorously that from Hamburger, so-called Hamburger moments problem, that if we increase the lambda, for lambda going to infinity, of course, we obtain the minimum and maximum will approach and coincide with the exact value. Okay, here is the plot presenting numerical data, and dotted line is exact line of exact solution. And then you see for various lambdas, starting from lambda 2, which gives only the you see here, only the upper value. Then to lambda 3, 4, you very quickly approach, the upper and lower limits quickly approach to this dotted exact line. And for lambda equals 10, you wouldn't distinguish on this graph the upper and lower limit. They will simply will be of the same difference as the thickness of this line, or even less. Okay, so this is the example which demonstrates the method. Now, let's try to apply this method, unless you have some questions, because this is really the simplest demonstration. And then we pass to more complicated problems and more physical problems. Essentially, the positivity of correlation matrix is the positivity of the measure of this integral. And somehow it completes the loop equations, which are not enough. You have one extra quantity to define. It completes the full system of conditions on solution. Okay, now we apply it again to some model which can be exactly solved, the so-called one-matrix model, which is this integral, single integral over the Hermitian matrix M, n by n Hermitian matrix M, with also the similar action, quadratic plus quartic terms. I forgot here the coupling G to write. It's G over 4. And in the large n limit. So when the matrices are very large, so-called Hooft limit, which can be expressed through planar graphs, which can be exactly solved in terms of when just passing from matrices to eigenvalues of the matrices and computing the saddle point. But we will test our numerical bootstrap method on this model. Again, for the moments, these are the moments already of this distribution, trace m to the L, normalized by n, because this is in the large n limit, the finite quantity. So we get a system, so-called loop equations, already slightly more complicated than the linear equations for the single integral. And here, the quadratic term, you can get these equations by simply implying the full, putting the full derivative, matrix derivatives inside of this integral. So it's also the invariance with respect to the shift of Hermitian measure. So you get this system of equations. Here you have products of two W's because you get products of traces under the average, and in the large n limit, products of traces factorize into average of product of traces factorizes into product of averages of traces. This is the main large property of the large n Hooft limit. Now, we again can solve this loop equation for all wk's in terms of the first non-trivial moment, W2. Then we impose the positive definiteness on the correlation matrix, which is simply this matrix, trace of M, K plus J. So it's a matrix of K plus J. And as such, actually, it also falls under the conditions of Hamburger moment problem. So you can really check that applying this method for the cutoff. So our cutoff is half of the length of W's, which you can meet here. So sending lambda max to infinity, we can prove using this Hamburger problem that we reach the exact result. But again, we can only have finite lambda, and we get inequalities, exact inequalities, in the sense that it's not as an equality, it's not an approximation. You can be sure that the exact result is between these two values in that sense. That's, by the way, the strength of this bootstrap method. In Monte Carlo, you have, of course, always the at least the statistical error, which gives you the interval. But in fact, you are never 100% sure that your value is not with a small probability, but outside of this interval, yes, of your margins. Here, it's really rigorous because all the relations we use are indeed taken without approximation. We only drop infinite many of these equations, but we use only those which are exact. Okay, then this is the plot of results. Again, dotted line is exact line. exact result for W2. This is all for this W2. And then you see how we approach the exact value when increasing lambda, the cutoff, the maximal momentum used. And you see something curious, which happens only in matrix models, not in single integrals, that you can even, this solution continues even beyond g equals 0 for negative g's. Which g is here? G over 4. For negative g, the integral is simply diverging, because you have, for it should be minus g over 4, of course. So for negative g's, in this case, the integral would be diverging. But in the larger limit, you can actually analytically show that the eigenvalues for g more than 0, when the potential is completely stable, the eigenvalues are locked in the potential well, the eigenvalues of the matrix. And they can penetrate well, but even for negative g's up to some g critical, the eigenvalues are also locked, and they can penetrate the wall only with exponential weight. That's why we drop it in the large n, exponential with n, e to the minus n. That it's also the standard picture in various large n matrix models or even quantum field theories, so that we can continue until this critical point when the first eigenvalue starts spilling over the top of this potential. Okay, so this is the situation with one matrix model. Things work smoothly here, and the results are, I don't give here the precision, but it's even on a small laptop, you can easily obtain 5-6 digits of precision here. Let's now pass to something more challenging, namely to the unsolvables, analytically unsolvable, even in the large n limit, two-matrix model. Yes?
So in the previous example, can you also get the critical exponent? Because usually that's more interesting than
yeah.
doubling.
In principle, yes. In principle, yes, we even, I think, tried it. Of course, it should, as we know, this quantity should diverge near this point as lambda minus lambda critical to 3 halves here. And you kind of see it, but of course you see the results near this point are worse and worse. The approach to the exact value is not so brilliant, but still we didn't try because it's somehow a toy model for us. We wanted to advance to something more challenging. But in principle, I think it's possible. The precision is quite high here. Okay. Now this unsolvable, analytically unsolvable two-matrix model. It's an integral over two Hermitian matrices, and both have these quadratic plus quartic potentials, like for the one matrix model, but we add also the interaction between them, which is commutator square with a new coupling H. And again, we don't study many different physical quantities here, but we wanted to demonstrate the method by calculating this integral in the larger limit. But of course, it's also a functional integral because the matrices are infinitely large, and already the method is tested on functional integrals before we pass to some realistic quantum field theory. Okay, here we introduce the matrix words. So the product of two matrices in various orders corresponds to the word with open external indices, with open indices. It's a matrix. So of course the number of words increases very quickly with the length of the word because you have many, many different combinations. And but we can write Schwinger-Dirichlet equations on traces of these words, on momenta corresponding to the words. Namely, we write this identity trace of full derivative of what we have under the integral is 0 for corresponding boundary conditions. For example, for G, for positive G, it's obvious that those are good boundary conditions. And we get loop equations relating various moments in this case, because everything is under the trace. You hit by this derivative the word or the action, and you get roughly this loop equation. When you hit by derivative the action, the potential, you get the derivative here, which is then and the trace of this derivative with the word, with this word. And then you can, when you hit the word, you split it in two. Because, say, here is the example. If you put a derivative here on this AB, if you hit A, you get this term. If you hit this A, if you had this A, that A, you get product of two traces. And due to the Lagrange factorization, which I mentioned already, you just write it as average of, as product of averages of traces. So this, and then the equations are closed on single trace averages here. This DAV, for example, is the following combination. So you get a number of traces of words slightly longer than the original word which we are having here. Okay, so in principle they are closed equations, but there are many, and the number of this equation increases very quickly with the length. And once we cut the length, the maximal length of words by some L maximum, we have many, more words than equations. This is a problem, so that some information is missing. What we should do, we now complete this information by positivity condition, which is the essential part of the matrix Bootstrap.
Yeah, the loop equation analog here,
What is the question?
I was asking.
So this equation gives that.
The loop equation analog is that.
Yeah, the loop equation, this is the general form, this is more explicit form, just term by term. Okay, so so then what is positivity of correlations here? Again, we do as we did for one matrix model, but we take a linear combination of all words up to a given length. Actually, by lambda, we denote 1/2 of maximal length of words which we meet, because in the correlation matrix, essentially, it doubles the length. Then again, trace of O dagger O for such operator is a positive definite quadratic form, so that we have the positivity of the following matrix, which is simply average of trace word K dagger times word J, as follows from here. So we impose the positive definiteness on the corresponding matrix. And in this way, we bootstrap the moments, all these moments, up to the moments of highest length. And the Bootstrap process reduces to the following semi-definite programming. So you minimize and maximize, find the upper and lower limit of the quantity, physical quantity you have chosen. It could be a linear combination of loops or one single loop. And it is subject to two loop equations, which are loop equations which don't contain the loops of higher length than L max. This is the rule. All other we drop because we don't want any approximations here. We want only to use the exact equations. And then the positivity of correlation matrix. But you notice here that we have already nonlinear equations. In the case of one matrix model, we can manage to solve them just recursively through one single quantity, but here, of course, no way to do it. And we have to deal with this problem, which is non-convex. So for any linear programming, it's terrible to have such a problem which is non-convex, because as you know, the non-convex manifold has, in principle, many extrema, minima or maxima. And once you fall in one of them, you don't know whether it's a good one. But the convex, almost the definition of convex manifold is that if you found the minimum, it's absolute minimum, or maximum, it's absolute maximum. That's why we have to do something, since we really want to make the length, the maximum length, as big as possible. What do we do here? And here we apply a so-called relaxation method for matrix loop equations. And let me describe what is it. So the idea is to replace the nonlinear loop equations by linear relations plus convex inequalities. Namely, this product of Wilson loops, I wanted to say of moments on the right-hand side of equation, this nonlinear term, we denote by a new variable, simply x, p, q. And then we treat these equations as linear, yes, because you replace it's for the moment it sounds very cheap, yes. You replace the product of two terms by new variables, and you get a linear set of equations. But of course, you have to impose some conditions on this matrix. And what we impose is the positivity of so-called relaxation matrix. This matrix consists of a row and a column of our momenta, and all these x's, like independent variables, are placed into the interior of this matrix, up to infinity, but of course, in our case, it's cut off by maximal length. And we impose the positivity on this R matrix. We don't know precisely why it works, and works quite well, this condition. And it is used in the literature, so we found it in the literature, people use it, but we never found explanation, and in particular for our problem, we don't have explanation why at all it gives something reasonable. The only thing I can say that once X becomes this product, what is our goal in principle, to be as close as possible to this relation, then the matrix has rank 1. It's completely degenerate. So it's in the space of all these variables where we will travel with our linear programming. It's a very strong cusp. It's sort of a corner into which the system wants to get. But of course, it's a very physicist's explanation, a very physical explanation, and not mathematical, rigorously mathematical explanation of the use of this relaxation method. But then, of course, we lose some information because we use inequalities instead of this equality, but it can be compensated by the fact that the problem becomes convex, and we can greatly increase L maximum, our cutoff. We checked it on a few models, including one matrix model, for example, and it's clear that it's worth applying this relaxation. So we transformed our nonlinear, non-convex problem to a convex one, and now I will show the results of application of SDP, semi-definite programming, to this model. First I show on the simplest possible example, on the lowest possible length, maximal length, how it works. So you write these 20 equations on 14 equations on 20 momenta. I don't put here averages. It's self-understood that that all these are averages of corresponding momenta. Then there are very few nonlinear terms, and they're only of this form on this step. And these x, they're equal because of the symmetry between A and B here. We look only on symmetric solution. And there are only 3 equations which contain this x. And then we impose relaxation in the simplest possible form. X is greater or equal to trace A squared square. In principle, we want the equality, but we impose the inequality. And it can be written in the form of this relaxation matrix, which is precisely the form I showed in the general case on the previous transparency. Here we impose relaxation in this simple form. And then, in virtue of now linear loop equations, all momenta and including x can be expressed through 7 basic ones. And we will look for this, we will do this minimization maximization procedure only by varying these momenta. There is also an important remark that we have some symmetries which we impose on our solutions. In principle, the solutions could have less of symmetry than the action. This is the symmetry of the action. So we have various sectors of even, odd, and even odd, according to the number of occurrences of A and B in the operators. And then the correlation matrix can factorizes into blocks. For example, even odd block is already much smaller than the matrix. So you, of course, you decrease the number of conditions, which is good, because the symmetry allows you not to work with huge matrices, but decrease the matrices. And say, even in this very low approximation, L max equals 4, we get already 1 or 1.5 digit precision in like 1/10 of a second on a small computer for some generic values of couplings. But now when we try already a longer run for the same matrix model, for these values, we obtain the precision. You see, this is the graph representing the islands where we should place trace the 4th momentum and the 2nd momentum. So it's, say, for L equals 14, this point is somewhere in this area. But then increasing the L max, these are L max, we quickly converge to very precise result, namely for L max equals 22, which is still possible on the laptop. We have 6 digits of precision here. This is this little point. And again, I stress that the inequalities are exact. unlike the Monte Carlo. And moreover, so we spent here 40 hours of CPU time for this computation, and it can be improved, as Zechon told me, but probably we didn't want to lose much time on this, again, sort of toy model. This gentleman did for us the Monte Carlo calculation of the same quantities. And as you see, to reach 4 digits, he needed 80 hours on his laptop. And of course, to get 1 more digit, it's the time, you need much more time than maybe 10 times more time to reach it. And so already on this matrix model, which I stress is a functional integral, it's more efficient than Monte Carlo, which should probably hint us on great possibilities, this method. And we passed to 10 minutes.
No, actually,
With, sorry, 45 minutes.
you should really, sketch this part. It's 45 in total. I should have told you at
Yeah, but 5 minutes at least I have, yes?
Yes.
Or
but,
7 even, because we started exactly at 3.
Yes, yes.
Yeah, okay.
Sorry, 45 minutes with questions.
Yeah,
That's
but
right.
5 minutes of questions. Okay, anyway, but it would be a pity not to say at least quickly what. So here we apply the method to McCain-Comigdan loop equations. So these pictures I shouldn't even explain you. So we are after the plaquette average, the basic quantity in lattice gauge theories to compute. The loop equations are written for loop average. Again, it's just the invariance of the measure with respect to the shift on the group. And the equations look, McCain-Comigdan equations look schematically as follows. So you apply for some loop, for a link on the loop, you apply this shift, and you get from action the plaquette attached with this and that minus that orientation, and some overall plaquettes about the link. And on the right-hand side, you hit already by this shift the Wilson loop itself, and it splits into 2 loops according to some obvious rules. So you have the equations in form very similar to the matrix model equations. But already we are on the lattice, and for L max, the length of our loops equals 16. We have about 40,000 loop equations in 3 dimensions and about 100,000 in 4 dimensions. And around 3/4 of them are independent. Only a small minority actually are nonlinear because the loops are small. So this, in the right-hand side, the nonlinear terms are quite rare. Okay, and then the positivity of correlation matrix is simply, we take the Wilson paths from 0 to some point x, all possible paths. We make a linear combination of these paths. And then again, we say that trace O dagger O of this operator, which is this correlation matrix of paths, but in fact it's a Wilson loop. Say you go this way, and with dagger you go back. So you get also the loop combined out of 2 paths. And you have positivity on this correlation matrix. I wanted to demonstrate it with shortest path, like you have this path simply around plaquette up and down, and the matrix looks as follows. And the condition of positive definite simply is like unitarity. The plaquette average square is smaller than 1 here. In practice, we use only the contours starting, so x is equal to 0 also. In principle, if we had infinitely powerful computer, it would be enough for the length of loops of infinite length. It's enough. We would list here all possible conditions. But we have L equals 16, and so reflection positivity. There are extra conditions similar to, I skip this transparency. They're similar to correlation matrix positivity, but using some symmetries, reflection symmetries of the lattice Wilson action. They are also very important. Then there is symmetry reduction, similar to what I showed for the matrix model. Of course, we have lattice symmetry point groups which are listed here with respect to various rotations and shifts, rotations essentially of our Wilson paths. And if we use the group theory to again block, diagonalize those huge correlation matrices. And here, for example, we have the correlation matrix, which is absolutely hopeless to directly analyze, 6,500. But when it splits into the blocks corresponding to particular representations of these point groups, then it becomes doable. And final algorithm also looks very similar to what we had in the matrix model. Like we compute, in this case, we compute just plaquette average. I will show the results. Then the loop equations we relax, we have only linear terms here. Then relaxation condition is imposed on this axis. And then various positivities, including the main positivity of correlation matrix. And all of them are linear and convex, or convex, all these relations. And say at L max equals 16, every data point takes about 20 hours of CPU time already on the station, and only half an hour for 3D. And we use the Mossack SDP package. Okay, now results very quickly, 1 minute. So here is two-dimensional theory, which has the advantage of being exactly solvable. This is this famous Gross-Witt and Vadia solution with phase transition at lambda equals 1 somewhere here. So you see, dotted line is exact solution, and our when we increase our lambda max, we quickly approach to exact solution. The best result, actually recent, already not published, is lambda max 24. So we have these two lines, upper and lower limit. Every time here it's upper, lower limit. So of course it's still not ideal, but much better than what we started from, maybe 10% of precision. Okay, then in 3 dimensions, we only can compare to Monte Carlo. So there are here Monte Carlo points, and also some perturbation theory, strong coupling and weak coupling perturbation theory. So everything to the left, from here to the left, it's strong coupling phase, and to the right, it's the opposite, weak coupling phase, and which is more physical, yes, and to the right, the strong coupling phase. So our best result is this blue line, which is maximum and minimum value. Notice that it works well for upper limit, better for upper limit than for lower limit. And now for dimensions, the problem of maximal physical interest. So we have here L equals 16. And you see there is a perturbation theory here. So we compared, first of all, we compared to Monte Carlo data. The most interesting points are these purple points, as we call them, from various papers, because only here you can measure physical quantities, because you are inside your correlation radius is much more than lattice step and much smaller than the characteristic size of the system. In our case, the characteristic size is L max, essentially, our IR cutoff. And, and then, surprisingly, our upper limit really follows the perturbation theory, 3 orders of perturbation theory in a very neat way. So what does it mean? I'm not sure, but that's what we have now. So we have to approach these purple points by increasing L max, and we have been working for a while on L max equals 24, which should really give much better results. But for the moment, we have purely technical problems. which are understandable in this case. All these programs like MOSEC, SDP programs are not adopted to such a great scale of the problem, and the memory, say, all this is missing. Okay, then probably I drop this transparency and show you the basic open questions and future problems.
Thank you very
Thank you.
much. Thank you very much.